Okay, and okay, so both are set. Okay, all right. So last time we ended our time by talking about monotone sequences. Yeah, so let's go up and see. So this is what I scribbled in the tutorial this morning. Okay, right. So we showed that every real sequence admits a monotone subsequence, correct? This is one thing that we proved rigorously. And so what is that we are going to do next? We were heading towards this. Yeah, so we noted long back that every convergence sequence is bounded, and the converse unfortunately is not true, that every bounded sequence is convergent. Yeah, so we are attempting to prove the next best thing, which is that every bounded sequence of real numbers admits a convergent subsequence. Yeah, is this okay so far with everybody present here? Is this okay? I don't hear any response.
Yes.
Yes, so I'll just write lecture 12. Yeah, and we start with this theorem. So what is the statement of this theorem? Every bounded sequence of real numbers has a convergent subsequence. Yeah, the sequence itself may not be convergent, but it definitely admits a convergent subsequence. So this theorem is due to two mathematicians by the name of Bolzano and Weierstrass. So this is called as the Bolzano-Weierstrass theorem. So in the morning, there were some network issues, but so far it is going all right. Are you able to hear me clearly?
Yes, ma'am.
Yes? Okay, all right. Very nice. Okay. Okay. Very nice. So let's quickly provide a proof to this result. So let's suppose that xn be a bounded sequence of real numbers. Yeah, so I'm considering a sequence xn of real numbers, and suppose that this is bounded. Yeah? What are we required to show? We are required to show that xn admits a convergent subsequence, right? Okay. But okay, so we will get there. But what is that we know? We know that by the monotone well, not the monotone convergence theorem, by the existence of monotone theorem, we know that every sequence of real numbers admits a monotone subsequence, right? So in particular, the sequence xn also admits a monotone subsequence. Yeah. So let me denote by the monotone subsequence by xnk. Yeah. So let us denote by x and k uh, so how should I write it? So let me just be very precise here. Shouldn't make any loose statements. Say that xn then xn has a monotonic subsequence. Yeah, so let me label it by xnk. Yeah. Okay. Now let's look at the subsequence xnk. This is either monotonically increasing or monotonically decreasing. We don't care which one it is, because what is it is given to us that the sequence xn is bounded, which implies that the sequence xnk is bounded. So it is bounded and monotonic. So the monotone subsequence theorem tells us that the sequence xnk, the subsequence xnk necessarily converges. Yeah. So I'll just write that down. Since this subsequence xnk is also bounded. Why is it bounded? Because the sequence xn that we started off, that itself is bounded. It follows from the monotone convergence theorem that the subsequence xnk is convergent. And that's it. We are done. We have been able to demonstrate a convergent subsequence of a given sequence. So is this okay? Is this part okay with everybody present here?
Yes, ma'am.
Yes. Okay. All right. So I think in the assignment problem there are a couple of questions which can be done applying the Bolzano-Weierstrass theorem. So now I think you should be able to take those problems on. Okay. I'll pause for a minute if there are any further questions. If not, then we will proceed to the next thing. Okay, so is this okay? Is this bit okay with everybody present? No further questions? Okay, all right. So I believe silence is yes. Okay, so let's go ahead. Yeah. So the next concept that I want to discuss today is Cauchy sequences. Now, where do these come into picture? Yes, please.
Now, a subsequence is always monotonic, right?
Not necessarily. Why is a subsequence always monotonic?
Because like xn k plus 1 is greater than or equal to xn k. I mean,
Sorry?
in the definition of subsequence.
No, let's look at this example. No, for example, if xn is let's say what this. So let's take xn to be the sequence xn to be given by 0, 1, -1, -2, -3, -4, well, -5, 6, 7, 8, 3, 2, 1, whatever, and things like that. Yeah, and I can choose x and k to be which one? So I can choose it to be 1, -1, -5, 6, 8, 2, 1, and so on. This is certainly a subsequence of a given sequence. This is this is not monotonic. Isn't it? The indices nk, if you are confusing that with those are strictly increasing.
Yes, ma'am. Got it.
Yes, so the subsequence xnk may not be monotonic, isn't it?
Yes, ma'am.
Yes, is that okay?
Yes, ma'am.
Yeah, all right. Anything else? Okay, all right. All right. So the thing that I want to discuss next is Cauchy sequences. Now, how do Cauchy sequences come into the picture here? Okay. So far, you know, what is that we know about convergence of a sequence? One is the definition, in which you say that a sequence, let's take a sequence of real numbers, it converges to a possible limit x naught if something happens, right? Okay. Or the other criteria that we know about convergence of a sequence is the monotone convergence theorem, yeah, that every bounded monotone sequence converges. And you can sort of evaluate the limit in that case as a supremum of a certain set or an infimum of a certain set, respectively. Okay. So in order, you know, in order to apply the definition of a sequence, we need to sort of know the limit to which it possibly converges beforehand. Yeah. So the idea of the Cauchy sequences is the following. We need to be able to decide whether or not a given sequence converges without the knowledge of the limit to which it may converge. Yeah, so what do I mean to say this? So let's see. When we define, yeah, okay, here I have a definition here. So when we define a sequence, well, here it is. So when we say a sequence xn converges to x naught, we say that you give me an epsilon and I will give you a positive integer n naught, such that all but finitely many points of this sequence live in this epsilon neighborhood of the point x naught some stage onwards. Okay, if I can play this epsilon n game each time, then we say that the sequence xn converges. Now, supposingly, I have no idea how to get hold of a possible potential limit x naught. Right? What is the next best thing that we can do? Yeah, we can talk about the terms of the sequence getting close to each other. Yeah. So, what do I mean by that? Let me sort of define it rigorously. Where do I write? Over here. Yeah. So, okay. Hey. So, here's the definition. So, as before, X is a set and D is a metric on this set, XD be a metric space. Yeah. And let's consider a sequence xn in X, and I'm trying to define when do we say this is Cauchy. Yeah. A sequence xn in X is said to be Cauchy with respect to the metric D if the following is true. Yeah. If for every positive epsilon there exists a positive integer n naught such that what happens, such that the distance between the terms of the sequence xn and xm can be made smaller than epsilon whenever n and m are both bigger than n naught. So just like before, the number n naught gives us a cutoff in the sequence after which all the terms of the sequence xn are close to each other. How close is determined by the fixed positive number epsilon. Yeah. So we don't have an a priori candidate for x naught. So instead of that, we are talking about the terms of the sequence getting close to each other. Yeah. So let's take up an example. Yeah. So is this definition so far okay with everybody present here? Is this okay?
Yes, ma'am.
Yes? Okay.
Yes, ma'am.
Okay. All right. So let's take an example if that helps. Let's take an example. So let's take the real line with the Euclidean metric. Yeah. Okay, and let's consider the sequence xn of real numbers given by xn as 1 by n for each n in n. Yeah? Okay. So I'll try to show that the sequence is Cauchy. Yeah. Let's see. So let's fix some positive number epsilon, and let's consider xn minus xm. Yeah, xn minus xm. Yeah, so in this case it is 1 upon n minus 1 upon m. Right? So we are to determine a cutoff such that this difference is smaller than epsilon some stage onwards. Okay. Okay. So what do we do? So here is one thing I can do. Yeah. So this difference is all less than equal to the sum 1 upon n plus 1 upon m. Right. Okay. And now what is that I want? I want the right hand side to be less than epsilon. Right. So I will say the following. Yeah. I will say that. Use the Archimedean property of R to get a positive integer n naught such that what happens? Such that 2 by n naught is less than epsilon. Now, where is this coming from? Then, for little n bigger than, so I'll just write it like this. So then for little m and little m, both bigger than this number n, m naught, right? What is going to happen? 1 upon n and 1 upon m, the reciprocals are going to be less than 1 upon n naught, right? So which means that xn minus xm, which is by our calculation upstairs is at most 1 upon n plus 1 upon m, is less than 2 by n naught, which is less than epsilon. Right? So what is that we have shown? We have shown that corresponding to epsilon positive, I'm just summarizing the above discussion, there exists a positive integer n naught such that what happens? The terms xn minus xm is less than epsilon whenever little n and little m are both bigger than n naught. Is that correct? Conclusion, the given sequence is a Cauchy sequence. Is this okay? This little example okay with everybody present here? Any questions? So shall I assume no questions and we go on?
Yes.
Okay. All right. Okay. Okay. So here's one example just to illustrate Cauchy sequence. But let's recall what is that we started off with. We were trying to sort of decide whether or not a given sequence converges without the knowledge of the limit to which it may possibly converge, right? So we need to sort of find out if there is some relation between the Cauchy sequences and convergence sequences, right? One way or the other, right? So let's see. Here is a proposition to this effect. So let XD be a metric space as before, and the claim is that every convergence sequence is Cauchy. Yeah? If Xn is a sequence in the metric space XD, and if Xn is convergent, then it is necessarily Cauchy in the sense defined above. It's convergent, then Xn is Cauchy. Yeah? So given a metric space XD, every convergence sequence is Cauchy. Yeah? So for example, if a sequence is not Cauchy, then it cannot be convergent. That would be a conclusion of this proposition. Correct?
Ma'am,
Yes.
this does not happen for every metric space. This only happens for R, na?
So let's see. My claim is this is true everywhere. Let's see. What
Okay.
happens? What is the problem if you go outside a metric space, outside R?
Now I just remember from previously that this does not happen everywhere.
Okay, let's see. Let's see. Yeah. Okay. All right. So my claim is that every convergence sequence is Cauchy. All right. So let us suppose that so let Xn let Xn be a sequence in X, and suppose that Xn converges to some point X0, right? We are required to show that Xn is Cauchy, right? Okay. So since Xn converges to X0, let's just write down the definition. Then so I was planning to sort of leave this as an exercise, but since there's a question, let me just do it. Suppose that, so what does it mean? That means that for any positive epsilon fixed, there exists a positive integer n0 such that all terms of the sequence xn live in the epsilon neighborhood of the point x0 after the cutoff stage n0. Correct? Okay. Now I am required to show that xn is Cauchy, right? So let's consider, what is that I consider? I consider the distance between xn and xm, right? Now I am given that the sequence xn is convergent, right? So one way to go about it is apply the triangle inequality, right? So no matter what the indices n and m are, the triangle inequality always holds, which means that the distance between xn and xm is always less than or equal to the distance between xn and x naught and the distance between x naught and xm. So if n and m are both bigger than the index n naught, then these two terms on the right hand side of this inequality can be made smaller than epsilon, right? Okay, so just to be very careful, I will make an epsilon by 2 here. Yeah, so I will say that for n and m bigger than n naught, the distance between xn and x naught is less than epsilon by 2. This is follows from the convergence of the sequence xn to the point x naught. And so each of these terms is less than epsilon by 2, which implies that, hence it follows that, what follows? It follows that for epsilon positive fixed, there exists an integer which is n naught, such that what happens? Such that the distance between xn and xm, by the triangle inequality is at most epsilon whenever n and m are bigger than n naught. Yeah, this is exactly saying that the sequence xn is a Cauchy sequence in the metric space xt. Is this okay?
Yes, ma'am. This is okay.
Yeah. Any questions?
Ma'am?
Yes, please.
Hello, ma'am.
Yes,
Ma'am,
please.
is
Yes,
the
please.
converse is also true?
We will come to that. We will come to that converse a little bit later. That's the next thing I'm going to talk about. But is this proof okay with everybody present here?
Yes, ma'am.
Yes. Okay. All right. So let's see an example in order to address your question about whether or not the converse is true in general. Let's take up this example. Okay, so let me consider x as the open interval 0, 1 and d as the induced metric from the Euclidean metric on R, yeah, which means that this distance is given by this for all points x and y in x. Okay, and let's consider the sequence as before, yeah, xn is 1 by n for each index n. So my question to you is the sequence xn Cauchy in the metric space xd in this example here?
Yes, ma'am.
Yes, it's exactly the same argument as above, right? Yeah, so this is something for you to check. Exactly the same argument that we discussed above. Check that the sequence xn is Cauchy in the metric space xd. Correct? Everybody with me up till this point? Now the
Yes,
next question is the sequence xn convergent in the metric space xd?
Yes, ma'am.
Okay, so what is the limit?
yes, ma'am.
So what is the
0.
limit? 0, but 0 does not belong to the metric space x, right? So the sequence xn does not converge in the metric space xd. Correct? So I would say it does not converge to a point of xd. Let me be just very careful here. Does not converge to a point of X. Correct? Is that okay? Everybody with me? So here is an example of a metric space XD and a Cauchy sequence Xn which does not converge. Is this okay?
Yes, ma'am.
Yes. So the upshot of this discussion is that the converse to the statement that we just wrote down, this proposition is not true. Yeah, that although every convergence sequence is Cauchy, the converse is not true in general. Every Cauchy sequence need not be convergent. Is that okay?
Yes,
Yes, ma'am.
Yes. Okay. Excellent.
Yes, ma'am.
All right. Okay. So that is the next thing. Yeah. So the question that we were addressing is so the question that we address is that is every Cauchy sequence convergent, right? That's the question that we ask, and the answer is no. Correct? That's the example that we just discussed. Correct? Is that okay?
Yes, ma'am.
Yes. Now,
Ma'am,
yes,
hello, ma'am.
please. Yes.
I just got a bit confused. I'm sorry. I mean, in the meantime, my internet connection got lost.
Tell
What
me.
I want to ask that 1 by n is not convergent. Xn is equal to 1 by n is not convergent.
Yes, yes. That's what I'm trying to say. It's not convergent in the metric space XD. Yes.
Isn't it converging to 0? I mean,
It converges to 0, but 0 is not a point in X. So it does not converge in XD.
okay, it's not
X,
converging.
yeah, X is open interval 0, 1.
Okay. I understand.
Correct? Yeah. Okay. So the conclusion of, upshot of this example is that every Cauchy sequence is not necessarily convergent, right? Okay, so maybe this was a very ambitious question to ask, and I am going to sort of redesign my question and ask, is every Cauchy sequence bounded? Right? Makes sense, right? This question makes sense.
Yes, ma'am.
Yes. So let's try to investigate, and it turns out that this is true, that every Cauchy sequence is bounded. Yeah. So let me write that down. So proposition. So as before, XD be a metric space. And let Xn be a Cauchy sequence in this metric space. Yeah, then the claim is, the theorem says that Xn is bounded. Okay, all right. So let's just quickly fill in a proof. Okay, so what is that we are given? We are given that the sequence Xn is Cauchy. That means that given any positive epsilon, there is a cutoff stage beyond which the terms of the sequence are epsilon close to each other. So in particular, I am going to take epsilon as 1. Yeah, so I'll just write it for clarity. There exists corresponding to this positive number 1, there is going to exist a positive integer n naught such that the distance between xn and xm is less than 1 whenever n and m are both bigger than n naught. Correct? Is that okay?
Yes, ma'am.
Yes. Okay. Okay, so let me make this. Yeah. So in particular, what does it imply? In particular, it implies that so I can fix, let n vary, and I can fix, instead of m, I'm going to plug in n naught. Yeah. In particular, this implies that the distance between xn and the term xn naught is going to be strictly less than 1, and this is going to hold whenever little n is bigger than n naught. Yeah, I've just fixed the second term here, xm. I fixed it as xn naught. Okay. Right. So what does it mean? It means that all the terms of the sequence xn are in this. So if you consider this open ball around the point x naught with center x naught, radius 1 in the metric d, then all the terms of the sequence xn beyond the stage n naught are in this ball, isn't it? Is that correct?
Yes,
I'm just
ma'am.
Yes, ma'am.
rewording the above statement, right? This is exactly, just notation here, right? Now, so what is that my claim? My claim is that the sequence xn is bounded, yeah, which means that, what do you mean by saying that the sequence xn is bounded in a metric space xt? That if you fix some point and you can find a large radius independent of the index n, such that all these points of the sequence xn are in that ball, right? So I've been able to account for all the points of the sequence xn after the stage n naught. What remains is, which are the points which remain to be sort of taken care of. So I need to take care of the points x1, x2, xn naught minus 1. Is that okay? Yes? Is that okay? Does everybody follow this?
Yes, ma'am.
Yes.
Yes. So consider the following finitely many points, right? Now, what do? I will take the distance between each of them. Yeah. So distance from the distance in the metric D between the point x1 and the point x0. Yeah. So I'm going to consider this. Correct? Is that okay? These are only finitely many positive numbers. Yeah, some of them may be 0, I don't care. Is that okay? Is that okay?
Yes, ma'am.
Yes. Now I'm going to take the supremum, so supremum or the maximum, whichever you want to call it, of all of these together with what? Together with together with 1. Yeah, and I'm going to call this number as R. Yeah. So then is it true that all the points of the sequence xn will lie in this ball centered around x naught of radius n? So now I have changed. So the difference between the above statement is, now I'm making the statement for all natural number little n. So is this correct?
Yes, ma'am.
Yeah, is
Yes,
this
ma'am.
okay with everybody present here? Yeah. See, only finitely many points were left, and they are not a problem at all because they are only finite. Is that okay?
Yes, ma'am.
Yes, excellent. So conclusion, every Cauchy sequence is bounded. we are done, right? Okay. So, you know, the idea of working with Cauchy sequences was to somehow sort of get a better control on establishing whether or not a sequence is convergent, but we could get only one-way implication. That is that every convergent sequence is Cauchy, but the converse is not true. Yeah. However, if we work with, instead of a general metric space XD, however, if we work with the metric space R, the set of real numbers with the Euclidean metric, then the converse statement also holds that every Cauchy sequence is convergent. Yeah, so I'll write that down, and you know, one should wonder what is so magical about R that it's with the Euclidean metric that things work fine there. So I'll just write down the proposition first. So I am now in the real line with the Euclidean metric. Yeah, please note this is true only with the Euclidean metric. If you throw in any other metric on the set of real numbers, the following result may not be true. Okay. So what is it I want to call? So this is the Cauchy convergence criteria. What did it say? It says that a sequence of real numbers So what I mean here is real numbers with the Euclidean metric is convergent if and only if it is a Cauchy sequence. Yeah. So every convergence sequence is Cauchy, but every Cauchy sequence in general need not be convergent. However, if you are working with the real line and the Euclidean metric, then every Cauchy sequence is also convergent. Yeah. So on the real line with the Euclidean metric, convergence sequences and Cauchy sequences are one and the same. Is this okay? The statement makes sense to everybody present here?
Yes, ma'am.
Yes?
Yes, ma'am.
Okay. Okay. So let's fill in a proof. All right. So there's one part of the proof that we have already done, right? That every convergence sequence is Cauchy. Yeah. So I will sort of leave that. That is done. That is true in general also. I'm going to look at the other part where we assume that the sequence xn is Cauchy and try to prove that it is convergent. Yeah. Is that okay? Let xn
Yes, ma'am.
be Cauchy on the real line with the Euclidean metric, right? We want to show that the sequence xn is necessarily convergent, right? Okay. All right. So what do we do, right? So in order to show that, you know, the sequence xn is convergent, we need to get hold of a possible limit, right? That's the only way to go about it. Right, so we need to get hold of a possible limit, right? So in order to get hold of a possible limit, now we need to find a real number to which this sequence is going to converge. Now how do we do that? So one way is the following. Yeah, so we appeal to the previous proposition which said that every Cauchy sequence is bounded. Yeah, so in particular the sequence xn is bounded. Yeah. So I'm going to write that down. Let's go one by one. So since sequence xn is Cauchy by assumption, it follows that the sequence xn is bounded. Correct? Now I have a Cauchy sequence which is bounded where in the real line with the Euclidean metric. So I have a bounded sequence of real numbers. Yeah, so I can now appeal to the Bolzano-Vistos theorem, which will tell me that the sequence xn admits a convergent subsequence. Yeah, so I'll write that down. Use the Bolzano-Vistos theorem. To get a convergent subsequence. So I'm going to label it by x and k. Say x and k of the sequence xn. Is this okay? Everybody with me? Everybody with me up till this point? So suppose that this subsequence converges to the point x naught. Is this okay? Everybody with me? Please ask if there is a doubt. See, why am I sort of interested in convergent subsequence? You know, I am given a Cauchy sequence and I have to prove it is convergent. So somehow I have to find a possible limit. This is one way I am isolating a convergent subsequence. And the limit of this, you know, now I'll try to prove that the sequence xn indeed converges to this point x naught. Is this okay?
Yes, ma'am.
Yes. Okay. Everybody with me up till this point? Any questions, please ask. Yeah. So I'll write that. We will show that. We will show that the sequence xn converges to x naught as n tends to infinity. Yeah, we are required to show this. Okay, but what is that we know? We know that the sequence xn is Cauchy. So let's use that information. Yeah, and we know that the subsequence xnk converges to x naught. So I'm going to write that down. So in order to do that, let me fix a positive epsilon in the first place. So suppose epsilon positive is fixed. Now, since the sequence xn is Cauchy, I'm just collecting what all information is given to me. There exists a positive integer n naught such that what happens? Such that xn xm, this difference is at most epsilon beyond the stage n naught, right? This is just definition of the fact that the sequence xn is Cauchy in the Euclidean metric. Okay. And what's the other thing that I know? I know that the subsequence xnk converges to x naught. I'm also going to write that down. So this subsequence converges to x naught. It follows that what follows? It follows that corresponding to this epsilon positive that is given to me, there exists some integer. I'm going to call it k naught, such that xnk minus x naught is smaller than epsilon whenever k is bigger than k naught, right? Okay, so if I'm being very careful, I'll just put a 1 by 2 everywhere. So is this okay? Everybody with me up till this point? I've just written the definitions that the sequence xn is Cauchy and the subsequence xnk converges to a point x0, right? Now, what is that I am required to show? I am required to show that the sequence xn itself converges to the point x0. Yeah, so I'm going to consider, what am I going to consider? I'm going to consider xn minus x0, right? So I'm going to label this statement as 1 and this statement upstairs as 2. Okay, okay. So I'm going to apply the triangle inequality, right? So I'm going to say xn minus xnj plus xnj minus x0, right? So at this stage, when I apply the triangle inequality, j is some, nj is some arbitrary index, doesn't matter what, this always holds true. Okay. Now, in order to appeal to statement 2, I need to make sure, I need to make sure both of these terms on the right hand side are small, some stage onwards, right? Is that okay? Everybody with me?
Yes, ma'am.
Yes. Okay. So in order to appeal to statement 2, I need to make sure, what do I make to make sure? That the indices little n and nj are both bigger than n0. Yeah. So for this term to be smaller than epsilon, I need to make sure that n and nj are both bigger than n0, right? And in order to appeal to statement 1, in order to make the second term small, I need to make sure that the indices j is bigger than k0, right? So there are 3 things that I want to make sure simultaneously, right? If that can be done, if n, nj, and j, n and nj are bigger than n0, nj is bigger than k0, then I'm done. Correct? Is that okay? Yes?
Yes, ma'am.
Yes. So I'm going to say the following thing. Yeah, please note that. I'm going to say that. So I'm going to say that there is a little j such that j is bigger than k0 and nj is bigger than n0. Yeah, then I'm going to make that claim. I say that there is a little j such that, let me write that down, such that j is bigger than k0 and nj is bigger than n0, right? If I can choose j like this, then what happens? Then for little n bigger than n0, I'm going to rewrite the inequality upstairs one more time. Xn minus x0 is xn minus, for this particular choice of j, each of these terms will going to be smaller than epsilon by 2 and epsilon by 2, and hence it follows that xn minus x0 is less than epsilon. So all the terms of the sequence xn live in the epsilon neighborhood of the point x0, provided little n is bigger than n0. Yeah, that is saying that the sequence xn converges to the point x0. Now the question is, why can I choose little j like this? Why can I always do that?
Ma'am, for j greater than equals to k0, we can say nj is greater than nk0. So
That much is true, correct?
so if we choose two numbers n and nj which are greater than some nk0.
See, if so, let me write this down here. So let's say k0 is here. Um, See, if K naught is, so what you're trying to say is, let me write this down. So what you're trying to say is that let's pick J bigger than K naught, then Nj is always bigger than J is bigger than K naught. Is that what you wanted to say? Was it Kritika? Is that correct?
Yes, ma'am. Yes, ma'am.
Yes, yes. Now this is true, right? So if, so I'll write some quantifiers here. If J is bigger than K naught, then Nj is bigger than K naught, right? But what do I want? Nj to be bigger than N naught. So if K naught is bigger than N naught, then there's no problem at all in your argument, right?
Yes,
Correct?
ma'am.
Correct. But what if K naught is smaller than N naught? For example, if I draw a picture like this, what if K naught is smaller than N naught? I say that even then this can be arranged. Why is that? This is because we are forgetting an important argument. This is because the sequence of Nj's are strictly increasing. Yeah. So N1, N2, N3, this is a strictly increasing sequence. You know, so at some point Nj's will hit the stage N0. Correct? So you can always do this. Is this okay?
Yes, ma'am.
Yeah, is this okay with everybody present here?
Yes, ma'am.
Okay, excellent. All right. So what is that we have established? We established that a sequence of real numbers with the Euclidean metric, yeah, is convergent if and only if it is Cauchy. All right. I think we should sort of take an example. We have been talking about some theory non-stop. It might be a good idea to take a pause and see an example. Yeah. So no questions so far. Shall we see an example? All right. Very good. So let's see an example. Okay. So let's consider a sequence given as follows. So I'm going to define it recursively. So let x1 be 1. And I need to tell you how do I evaluate the n plus 1th term of the sequence. I say that this is defined as n. Right? Okay. So the question is the same, right? Let's consider the sequence xn of real numbers. Evaluate whether this sequence, if at all the sequence is convergent, evaluate the limit. If not, give me a reason. Correct? So let's start by finding the first few terms of the sequence, right? So x1 is 1, that is given to us. X2 is 1 plus 1 by 1, this is 2. X3 is 1 plus 1 by 2, it is 3 by 2. X4 is 1 plus 2 by 3, right? So this is 5 by 3. And x5 is what? X5 is 1 plus 3 by 5, it is 8 by 5. Correct? Okay. So unfortunately, this sequence xn, as we compute the first few terms, we see that the sequence xn is not monotone. Correct? Everybody sees that?
Yes.
Yes. So we don't know, we don't know how do we go about it. Yeah. But what is that we know? There's one little thing that we can say, that the sequence xn is strictly positive for each n. Yeah, this is bounded below. That much we can say. Correct? So you sort of try an argument using the principle of mathematical induction. That can be done. Okay. So let's see and try and see whether this sequence xn is Cauchy, right? So in order to say that the sequence xn is Cauchy, one should work out the difference xn minus xm, right? But over here, the sequence is defined recursively in terms of the n plus 1th term is defined in terms of xn. Yeah? So it will be much wiser to sort of look at xn plus 1 minus xn first. Yeah? So what am I trying to say? I'm trying to say that let's consider the difference xn plus 1 minus xn first. Yeah. So what is this? This is by definition. So this is 1 plus 1 by xn, and the second term is 1 plus 1 by xn minus 1. Correct? So this is 1 upon xn minus 1 upon xn minus 1. Right? Let's see if this helps us in any way. Right? So this is xn minus 1 minus xn divide and downstairs in the denominator I will have this product xn times xn minus 1. Okay. Okay. So let's see what can we do. Let's look at this. So xn times, so consider this term, yeah, xn times xn minus 1. This product which I have in the denominator, this is by the definition. So I'm writing the nth term as 1 upon xn minus 1 plus xn minus 1 times xn minus 1. What is the advantage? The advantage is that this is xn minus 1 plus 1. Is that okay? Yeah. So far, what is that I can say? I can say that xn minus 1 is at least positive. So this term is bigger than 1. Yeah. But if I say bigger than 1, that doesn't help my case. So let me make a stronger statement here. I'll sort of add another bullet here, and I'll say that, in fact, use the principle of mathematical induction to show that it is bounded below by actually 1. Yeah, so I'll leave this for you to check. Yeah. Okay. See, how does this help me? So if I have 1 as the lower bound, then I can say that this product is bounded below by 2 for each index n. Well, this makes sense only for n bigger than 2. So I'll just quickly make that change. Right. So if I use this information in the calculation that I was doing above, that will tell me that the difference xn plus 1 minus xn is, so it follows that I'm going to club these two observations and make the following statement, that the difference xn plus 1 minus xn is at most, so I have upstairs, I will have xn minus 1 minus xn, and in the denominator, I've been able to find a lower bound for this denominator, which means when I take a reciprocal, I will have a 1 by 2. And this is true for each n bigger than 2. Correct? Is that okay?
Yes, ma'am.
Yes? Okay. Now, what is an advantage of a relation like this? See, I'm interested in finding xn minus xm. Yeah. So let's see. Let's sort of spend some more time on this. So now, let's consider. So I'm going to sort of repeat this argument one more time. So I'm going to consider the difference xn. So repeating exactly the same argument as above, this is going to tell me that this is xn minus 1 minus xn minus 2 by 2. Correct? Yeah. Which means that if I put together the above two observations, it will follow that xn plus 1 minus xn is less than or equal to xn minus 1 minus xn minus 2, and denominator I will have a 2 square. Correct? Is that okay? I'll just combine the above two bullets here. Is that okay?
Yes, ma'am.
Is that a yes with everybody present here?
Yes, ma'am.
Yeah. So, you go on like this. So if you continue this procedure like this, one can see that I'll sort of leave that for you to figure out. Now you write xn minus 1, right? Now you write down the difference xn minus 1 and xn minus 2 in terms of xn minus 2 and xn minus 3, and go on like this. So ultimately, what you will get is xn plus 1 minus xn. This difference is at most, so I will have x2, is that correct? Minus x1. And what should I have as the power? So if it's 2 square here, so each time I pick a power, which means that the power that should reflect here is 2 to the power n minus 1. So if my calculation is right, this is what I get. Yeah, but x2 is 2 and x1 is 1. So this is exactly 1 upon 2 to the power n minus 1. Yeah, and this is true for each index n. Is this okay? Yeah. So if you like, you can prove this statement again using the principle of mathematical induction. Put a small question mark here. This is something for you to check. Is this okay? Can I leave this for you to check?
Ma'am, till this far we are right, but what are we showing? Is it Cauchy?
We are trying to show it's Cauchy. See, we are interested in this. Yeah, we are interested in this difference, xn minus xm.
xm minus xn. We'll consider that and then we'll go on. Yeah.
Correct. But the way the sequence is defined, you don't end up anywhere, right? You have to sort of look at xn minus 1 and things like that, right? In order to, right? So that's what I'm trying to do. Yes?
Yeah. Yes, ma'am.
Yeah, so that's what I'm trying to do. So let's consider with this background. Yes, please.
Ma'am, when we have considered xn minus 1, shouldn't it be xn minus 2 minus xn minus 1 by 2 square?
Where? Over here, this first line, this inequality here, so I'm calling it A. So this inequality A, is it?
Ma'am, the previous bullet.
A previous bullet, xn minus, so you're saying this should be, what is that it should be?
Xn minus 2 minus xn minus 1 means drawing analogy from the previous one.
Doesn't matter, no, I am sort of put a absolute value here. Which way you take the difference doesn't matter, isn't it?
Okay.
Correct? Is that correct?
Yes, ma'am.
Yes, doesn't matter, no, because it's an absolute value. Correct?
Yes, ma'am.
Yeah, is that all okay, or did I make some mistake?
No,
Seems
ma'am.
okay. Seems okay,
Yeah.
right? Okay, all right. Okay.
Ma'am?
Yes, please.
Ma'am, what did you ask us to prove with induction? That question mark.
So the first thing is, there are two things here. First is this lower bound, that xn, each term in xn is at least 1. That is one you can prove by induction. And the last statement, that this inequality holds. You can use this, prove this by induction as well. that xn plus 1 minus x.
Inequality recursively, right?
Correct? Sorry?
We are getting this inequality recursively, right?
So getting this recursively, you can also prove this by mathematical induction.
Okay.
Correct? That's all I'm trying. So there's a question mark because I have not checked it here. I've just written it here without a proof.
Okay.
Yeah, I can leave this for you to check. Is that okay?
Okay, ma'am.
Yeah, okay.
Ma'am,
Alright.
we'll have to check this again with induction.
Yes.
Okay.
Yes. Okay. So let's try to establish that this is a Cauchy sequence. So in order to do that, I'm going to consider the difference xn minus xm, and let's take one of them to be bigger than other, right? So let's take m to be bigger than n, if you don't mind. So let's consider for this difference for m bigger than n, so that I will apply the triangle inequality now, right? So I'm going to write it as, I'm going to introduce a term xn plus 1, right? So I'm going to write it as xn plus 1 minus xn plus 2, right? Plus xn plus 2 minus xn plus 3, and so on, yeah, so on until I hit m, right? So for that, the last one would be m minus 1 minus xn. Is that correct? Is that correct? Everybody agrees with
Yes.
me? Yes? Okay. So if you like, you start from here and then go back and do the calculation that we did above. Some or the other way you have to do that, because that's how the function is defined, the sequence is defined, right? So appealing to the calculation that we did above, the first term here is at most 1 upon 2 to the power n minus 1. The second term would be at most 1 upon 2 to the power n, and so on. The last term would be 1 upon 2 to the power m minus 2. Is that correct?
Yes, ma'am.
Yes. Now, this is a geometric series with common ratio, things like that. You can sort of evaluate that. So, I am working under the assumption that m is bigger than n, right? So I'll sort of, one can take this common and you will get a 1 plus 1 by 2 and to the power m minus n minus 1, if I am correct, right? And this again geometric series with common ratio 1 by 2, so this is to the power n minus 2, right? So conclusion, anyways, the conclusion of all of this discussion is that what happens, that what is that we have been able to show, that for m bigger than n, we have been able to show that the difference xn minus xm is at most to the power n minus 2. Okay. All right. Now, in order to show that this is Cauchy, what remains? So, for epsilon fixed, so for epsilon positive fixed, how am I going to choose my positive integer here? I'm going to choose the positive integer so that the term 1 upon this term on the right is less than epsilon, right? So 1 upon 2 to power n minus 2 is less than epsilon, right? Right. So what does it mean? So that is exactly saying that 1 upon 2 to power n is less than epsilon by 4. Is that correct? Yeah, so I'll sort of, let me just write down clearly. So choose, so I'll just write it, choose capital N naught such that whatever I have written in this holds whenever little n is bigger than n naught, right? So then then for this fixed epsilon positive and m bigger than n naught, xn minus xm is always less than epsilon, right? Which tells me that the sequence xn is Cauchy in the is Cauchy, right? Hence the sequence xn is Cauchy in the metric space Rd in the Euclidean metric with the on the real line, and by the Cauchy convergence criteria, it follows that that the sequence xn is convergent as well. I'll just write that down. By the Cauchy convergence criteria, sequence xn is convergent in the metric space Rd. Is that okay? Is this okay with everybody present here?
Yes, ma'am.
Yes, and now you can write down the limit as x and use the recursive relation as upstairs, which defines this to evaluate what is x, right? Right? That is something everybody can do, I'll just say, I will say that evaluate limit of the sequence xn. Right? That is something that I'll leave it for you to do. All right? Is this bit okay with everybody present here?
Yes, ma'am.
Any questions? I'll pause for a minute. Okay, so is this okay with everybody? Everybody with me up till this point?
Yes, ma'am.
Okay, excellent. So, this is what I wanted to say about Cauchy sequences for now. We will come back to Cauchy sequences when we sort of take up topology, general topology a little later. Okay, so maybe I will sort of go on to the next thing, which is, so far we've been talking about convergence in two real numbers. Yeah, so the next thing is convergence. Maybe I'll just make one definition and stop. Convergence in the extended real number system. Yeah, so you remember we introduced two symbols and considered the extended real numbers. Yeah, so we want to talk about things like when do we say that a sequence xn of real numbers converges to positive infinity. So here is a definition. A sequence xn of real numbers is said to converge to positive infinite if something happens. Yeah? If for each real number m, there is a positive integer such that the terms of the sequence xn are bigger than this fixed positive number m beyond the stage n naught. All right. Yeah. And once we have understood this, I'll make a similar statement. So when do we say that a sequence xn of real numbers converges to negative infinity? So the sequence xn of real numbers is said to converge to negative infinity if the sequence minus of xn converges to positive infinity. Right? I think I'll stop right here for today's session, and next time we meet, we will continue with some examples. Okay. All right. I just announce before ending today's session, I will just announce that we all agreed for the first quiz on Monday, September 28th. I will also write an email on Moodle just to reach any student who missed out both the morning and the afternoon sessions. And the portion is all topics covered till now, including the reading assignments and tutorials and things like that. Okay, so I think from now, my end, I will stop this meeting for now. And of course, I am here. If you have any questions, then we can take them up. If not, then